This is day 1 of section 4.4, and we are still addressing this question as we will be for the entire unit for 4. The derivative, what is it good for? So what we're going to look at, when I say derivative, you're thinking slope. And so today what we're going to do is we're going to answer the essential question: how can derivatives be used to maximize and minimize values? So we are looking for maxes and mins on the function that you're working with. So the derivative is good for finding maxes and mins. Okay, so when we want to find maxes and mins, we call that process optimization. Okay, so it's a strategy for solving for maxes and mins. Okay, so here's kind of a quick review, or a quick outline of how we go about doing that. We want to read the question for understanding. So in other words, we want to read carefully, we want to identify information that we need, and we want to identify information that we have. We want to develop a mathematical model. So that's going to involve drawing a picture, labeling it, introducing a variable to represent a quantity to be maximized or minimized, and coming up with a function to differentiate a relationship between our variables. Then we want to graph the function, so we want to get a sketch of that in the appropriate domain, and keep values that make sense, get rid of values that don't make sense. I'll elaborate more about that as we go through. Identify critical points. So remember from the last section, critical points are those points where the derivative is 0 or the derivative is undefined. So those are our hills, valleys, cusps, and corners. And then we have to identify the endpoints if we have them. And then we need to solve the model. So we go back to that model we created in step 2, and we solve that mathematical model using differentiation. And then we give meaning to the solution, so we interpret the solution. So let's, for instance, take this problem. So we're reading for understanding here. We have 40 feet of fence. So if you go to any home improvement store, you know that metal fencing is sold in rolls. And when you unroll it, typically we have, when we unroll that fence, we have 40 lineal feet of fence. And we want to use that fence, that bundle that we bought at the home store, to enclose a rectangular garden along the side of a barn. So for this garden, we want to make it as big as possible. So we want to maximize the area that we can enclose with that one bundle of fence. So for instance, as we're unrolling this fence, we can start propping it up against the side of the barn, and we would have something that looks kind of like that. So if you notice, we're creating some sort of rectangle, and we're not using the fence. If I backspace here, we're using the fence for the left and the right side, and we're using a fence for the front, but we don't need a fence for the back because that's the wall of the barn. So altogether, those 3 pieces of fencing are going to equal 40 feet. So that's going to give us then, if we look at the barn from above, that's going to give us this sort of area, okay, where we have the edge of the barn here, and then we have the fencing here. And so that 40 feet then ties into this length plus this length plus this length. So the first thing we want to do is we want to assign this shape some variables. So we'll call this y, we'll call that x, and if this is x, then this is also x. And now we can start coming up with a mathematical model. So we always need 2 mathematical models. We need an optimizing model, and then we need what I call a constraint. So a constraint is something that restricts what you can do. And so for instance, in this case, the restriction is that we only have 40 feet of fence. So this is our constraint function, is that x plus x, or 2x plus y, equals 40. And then we also have an optimizing function. So we'll talk about that in a second. So what I did here is I solved for y. Y equals 40 minus 2x. And I'll explain why we need that in a little bit. Okay, so now we have this optimizing function. So what is the maximum area that you can enclose? So our optimizing quantity is area. And so we know that when we take a look at this garden here, that shape is a rectangle. And that area we can find by multiplying the length times the width. So x times y. And notice we want a optimizing function in terms of a single variable. And in this case, I want it in terms of x. So this is not a single variable, these are two variables. So that's where this is going to come in handy. Now that I know y equals 40 minus 2x, I can substitute that in here and get my area function in terms of a single variable. So we know that y is 40 minus 2x, and so I can rewrite area as x times 40 minus 2x. So simplifying that, our area is 40x minus 2x squared, and that's what we want to maximize. So this is the expression, this area function, this is the expression that we want to maximize. Maximize means I want to find on this function, I want to find the hill of this function. So if we notice this function is an x squared, so it's a parabola, and it's a minus x squared, which means it's an upside down parabola. I want to find that hill. That hill is going to maximize my area function. So just a quick visual, it looks something like this. I didn't put numbers on the axes intentionally because we're going to find those analytically. And so there's my maximum value. And since I'm graphing my area function, if I go over to the y-axis, this would be my maximum area. And then I can find the value for x that maximum area occurs. And if I can find that value for x, then I know these lengths of my fencings. And then I can find the remaining length. Okay, so to find this maximized location, that's where the strategies from the last section come in. Because we know to find maximums, we know to find hills and valleys, we can take the derivative and set it equal to 0. So we're going to go ahead and do that. The derivative of 40x minus 2x squared is 40 minus 4x. And we're going to set that equal to 0. And then we'll take the 4x to the other side. So we know that setting it equal to 0 is identifying this flat spot on the function. That's where we have 0 slope, because we have 0 derivative. And when I say derivative, you're thinking slope. And so when we solve that, we get an x value of 10. So we know then that when x is 10, we've maximized our area. Okay, so we have 10 and 10, and if we put 10 here, we should have 20 here. So 10 plus 20 plus 10 is 40 feet of fencing. So we know we have a width of 10, we have a length of 20, which means we have a maximum area of 200. Okay, so if I put that in, we've got a maximum area of 200 square feet. So it's the biggest garden that we can make with 40 lineal feet of fence. Here's another optimizing problem. So we're reading for understanding again. It says find two numbers whose sum is 20 and whose product is as large as possible. So I mentioned in the last example, we always have two equations, a constraint and an optimizing function. And so when we're reading this, we see we need variables for two numbers. So let's call them x and y. So our constraint is that their sum, or when we add them together, their sum is 20. So here's my constraint. This is my restriction. Is whatever these two numbers are, they got to add to 20. And then we're going to optimize the product. So I'm going to call the optimizing function p of x, p for product. And again, it's p of x because I want to have a single variable to represent this function. And we know the product is multiplying two numbers together, x times y. This is two different variables, so I'm going to have to come up here and solve my constraint for y. So when I do that, I get y equals 20 minus x, and now I can substitute that constraint in here and get my product function in terms of one variable. So my product function is x times 20 minus x, and I want to maximize that. So here's my product function. Here it's graphed. So if we distribute the x, we get 20x minus x squared. So we can see that this function again is a parabola that's upside down. So it's going to look like this. And again, I have not labeled my axes, the numbers on my axes, because I want to find the answers analytically. I just want you to see the basic shape. And so, so to maximize this, we know that the strategy for maximizing is finding that hill. And that strategy is taking the derivative and setting it equal to 0. So when I do that, the derivative is 20 minus 2x. I'm going to solve that. I get an x value of 10. And if my x value of 10, then my y value is also 10. So in order to have this constraint of being the sum of 20, I need a 10 and a 10 product, and that's going to give me the maximum product, which is 100. So on this graph, then I would have at this vertex here, this maximum location, I would have on the y-axis, I would have a product of 100, and on the x-axis, I would have a value of 10. So right there's our maximum product, and our location is an x value of 10. Okay, so here's another example. This one's getting a little more complex. So way back in the day, we used to buy cans of oil for our cars. Now they're in plastic containers, but we used to they used to be metal cans that looked like soup cans, but a little bit bigger. And so if you are a manufacturer that would make these cans, you might have this conundrum to deal with, and that is finding the dimensions for a 1 liter cylindrical can that will use the least amount of material. So to maximize your profit, you want to make sure you control your costs. And since more steel would cost more money, if we can use as little as possible, we can minimize that cost. So our constraint here, if we're reading for understanding here, our constraint might be a little tough to pick out, because looking at this, it feels like we don't have any numbers to work with, but we do right here. 1 liter is a measurement of volume. So we know that can has to hold exactly 1 liter of oil. Okay. So, and then this is a minimizing question. Least amount of material is to minimize something. And when we're talking about using material, we're talking about minimizing the surface area of the can, so that we're cutting out as little metal as possible. So let's talk about the setting up this optimizing function. So if you remember from geometry, the shape of the soup can sort of shape is a cylinder, and its surface area is the top and the bottom plus this curved surface. And this curved surface, if we cut it, is actually a rectangle that is as tall as this purple and as long as the circumference, as I go around the top here, the circumference of this can, so 2 pi r. So we have 2 pi r squareds, that's the top and the bottom. And then to that we're going to add 2 pi r, that's the circumference of the top, times the height, which is that rectangle that we can unroll. And so we want to minimize that. So that's the area of the top and bottom, and that's that's what we used in geometry call the lateral area, or the area of the sides. And so, so there's our optimizing. We want to minimize this. And now we need that other equation that has to come back here and deal with our constraint of 1 liter. So since 1 liter is volume, our optimizing equation is the volume equation, which is pi r squared h. And so now we have to get the volume into the right units. So 1 liter is 1,000 cubic centimeters. And we need to get into centimeters because we measure this can. We'll measure the height and the radius of this can using a ruler. And rulers don't measure in liters, they measure in centimeters. So 1 liter is 1,000 centimeters. So our constraint is that we need a 1,000 cubic centimeter volume, and the volume is equal to pi r squared h. So the way we use this constraint is to come back up here, and you notice that this area model has, we want it in terms of a single variable r, but we have an r and an h here. So we're going to solve this for h, the volume equation for h, and substitute it in to our height here in our minimizing function. So when I solve this for h, I get 1,000 over pi r squared, and I'm going to put that right here to get rid of the h. And now I'm going to simplify this. So I've got 2 pi r squared, and then the pi's cancel, and one of the r's cancel. So I've got 2 pi r squared plus 2,000 divided by r. So here is my optimizing function. And so this is obviously more complicated. It's not just a parabola. It's something that looks way different. Looks like this. So it's kind of parabolic-ish. It's kind of got that curve of a parabola, but it's got also the bend of a 1 over x sort of look, if you can kind of envision that. And so the minimum is about right here. So that's what we're going after, is where is that slope? Where's the derivative equal to 0? Where's the slope of that tangent line horizontal? Okay, so we're trying to find that. So that being the case, that means I have to differentiate this. And in order to differentiate this, I'm going to rewrite the fraction as 2,000 r to the minus 1. That's going to help me use my power rule for differentiation. So now I can go ahead and take the derivative. So remember, 2 pi, that's just a constant. That's 2 times 3.14. So 2 pi is about 6.28. Okay, so when I'm taking the derivative here, I'm going to bring down the 2, make that 4 pi, and then times r. There's my power rule for my derivative. And then plus 2,000, bring this down, times negative 1 to r to the 1 smaller, which is negative 2. So I've got minus 2,000 r to the minus 2. So there's my derivative, and I have to set that equal to 0. So I've rewritten my derivative, 4 pi r minus 2,000 over r squared, because that's what negative powers do. They get relocated. And when I set that equal to 0, I'm locating that green point on the graph. So now I have to solve this, and this might look a little daunting, but it's really not that bad. So if we look at solving that, so we know that this is the expression to find this horizontal tangent line. So to solve that, I'm going to bring the 2,000 over r squared over to the left, make it positive, and then I'm going to treat the right-hand side, I'm going to clear fractions by multiplying through by r squared. So I've got 2,000 equals 4r cubed, and then, or 4 pi r cubed, excuse me. Then I can divide by 4 pi, and then I can cube root it, right? Cube rooting means taking it to the 1/3 power. So obviously this is a calculator question at this point. So we're going to go ahead and we're going to put that into our calculator. We're going to get a radius of 5.419 centimeters. So that's this location on the graph. That's 5.419 centimeters, okay? And that's going to minimize my area. In other words, minimize the amount of material I need to use. So what does that give me in terms of height? Well, I go back to my constraint equation, and it's been rearranged to solve for height. And I plug in that radius, and I get a height of about 10.84 centimeters. So I know I need a can that has a radius of 5.419 and a height of 10.84 centimeters. That's going to be the can that uses the least amount of material. So at this point, you should have enough to kind of get started here with day 1 of the optimization and modeling homework. This units, or this section spans 3 days. So if you're looking to do a proficiency quiz instead of completing the homework, then I would wait until day 3 when we learn some other aspects of optimization.